Hello, and thank you for tuning in once again to your Back-Ass Words Weird World. This is a little compilation video that I put together as far as some things that I had seen in the media and online and on YouTube of things that kind of point in the direction of supporting the idea that scientists and science is learning that what they'd previously thought about black holes and the way they were formed and the way they progress was not all-encompassing and correct. They're finding out new things about these black holes. This is a little compilation video. Some of it even seems, to me anyway, like it could be almost soft disclosure of something similar to a black hole being nearby. Anyway, let you guys check it out and see what you think. Here it is.
Stephen Hawking applied quantum physics to black holes and predicted that they wouldn't be black but would glow with heat radiation in a very distinctive way.
This is what astronomers look for. Not the black hole itself, but stars caught in the black hole's incredible gravitational pull. This one is tearing apart a star that drifted too close. A feeding black hole is anything but black. The whole star is wrenched out of shape as the monster tugs at it. Gas from the star whirls around the hole. It forms a superhot disk of star nearly 100,000 kilometers across. It's a deadly embrace that will last millions of years. What the black hole can't swallow, it belches out. Huge jets of uneven star are spat out into space. But what about the black holes that aren't feeding? Where are the millions of black holes that should be wandering through our galaxy? They remain hidden against the dark background of space. Luckily, there is a way of tracking even the blackest of black holes. And this is what gives them away. Light. A black hole's gravity is enormously powerful. It affects everything around it. It can even bend light. So when a black hole passes in front of a distant star, the light from that star is distorted. And the black hole gives itself away.
First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from those stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted like a funhouse mirror. So rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. A gravitational field not only warps space, it also warps time.
If black holes were made in the Big Bang with a mass of about that of Mount Everest, these black holes ought to be going pop about now.
There might be other ways to see a black hole. These particles, called cosmic rays, slam into our Earth's atmosphere with enough energy to create miniature black holes. These mini monsters would decay immediately in a shower of particles, but they are very difficult to observe.
We're almost at the store. The emittances look good.
Okay.
What if you could produce collisions this powerful in an Earth-bound lab and under controlled conditions actually create a black hole?
Now, first things first, mathematically speaking, anything could become a black hole if you were to compress it into a small enough space. That's right, you, me, this camera, everything in the universe has what is known as a Schwarzschild radius, a tiny, tiny amount of space that, were you to collapse the entire mass of the object into, its density would be so great that its gravitational pull would be so great that not even light could escape from it. You would have a black hole. If you were to compress Mount Everest into something smaller than a nanometer, you would have a black hole. And if you were to compress the entire Earth down to the size of a peanut, you would have a black hole. But fortunately for us, there is no known way to compress Everest or Earth in that fashion. But a star.
Start collimating a blue ring.
It's hoped that taking two very high-energy small pieces of a very fast proton and colliding them with each other, you can put enough energy into a small enough space that you can actually create the conditions by which a black hole would form. These black holes are supposed to be very small, therefore very hot.
Physicists are using advanced technology to blast gold atoms in opposite directions down giant tunnels almost 2.5 miles long. They accelerate these atoms to within a tiny fraction of the speed of light. the atoms collide, a fireball erupts. Sophisticated sensors record a splatter of subatomic particles, a hot soup of gluons and quarks.
What we believe we're creating is temperatures approaching 2 trillion degrees centigrade. That's 100,000 times hotter than the interior of the sun.
It's as if they are running the universe in reverse, taking us back to an instant when it was extremely hot and dense. Creating a black hole, it seems, will take even more energy than that. In fact, more than any Earth-bound collider can pack.
But fortunately for us, there is no way to compress Everest to Earth in that fashion. But a star,
That is, unless there's more to our universe and to gravity than we've thought.
Our injection efficiency looks good. The orbit looks good. Orbit RMS is under 2 millimeters in each plane.
Einstein's theory of general relativity is the one that we find in all the textbooks, and it's the one that we're all sort of pledged to defend, but it would be rash to say it's the last word on the subject of gravitation. And there are certainly alternative theories around, and some of them are quite popular, and some of these theories, these are non-standard theories of gravitation, predict that you could make a black hole by colliding together subatomic particles.
Time ever, astronomers might have witnessed a star actually become a black hole right before our eyes, or telescopes. In this visible light image from the Hubble Space Telescope, we can see a large star about 25 times the mass of our sun, around 22 million light years away in the galaxy NGC 6946. This was in 2007, but in a Hubble image from 2015, looking with the same filters at the same wavelengths, the star appears to be gone. One possible explanation, the star died and became a black hole. But it gets weirder. The most prevalent theory for how a black hole forms is through a supernova. If a star is big enough, at the end of its life, it will eject its outer layers at high velocity in a massive explosion, while the inner core collapses into a very tiny space, creating a gravity well so great that light can't escape. Literally a black hole. So did we see the star go supernova? No, not really. A team of astronomers was monitoring the star with a large binocular telescope in Arizona and saw the star get brighter in 2009, but not nearly as bright as a supernova. They call it a failed supernova. The star does expel its outermost layer, but relatively gently and not in a big explosion. With the Chandra X-ray Observatory, which would be able to reveal X-rays being emitted by the gas falling into the black hole. The team also wants to continue monitoring the star's location in visible light with Hubble, and will want to look at the location with the upcoming James Webb Space Telescope to check if there's a surviving star hidden by cooler dust that can be observed with Spitzer. So if this really is a black hole birth, what does that mean for astronomy? First of all, this would show that a star doesn't need to go supernova to form a black hole. Percent of massive stars don't go supernova, and they're still able to simply form a black hole. If future observations confirm this team's findings, this would be the first birth of a black hole ever witnessed and the first failed supernova ever discovered, both of which would usher in an exciting era of astronomy research.
Some scientists believe they may be able to create one at a new and more powerful system in Europe called the Large Hadron Collider. The key lies in whether the world we know is part of a more complex cosmic reality, beyond the 3 spatial dimensions plus time that we experience in our everyday lives.
Causing disturbances that propagate up to where we are. We could feel it happening. We could essentially see our universe around us changing, but we look around for the cause of it and we won't know what it is.
The idea is that a number of extra dimensions actually intersect our world.
10, 12 pi.
Okay.
When particles collide at very high energies, those extra dimensions enhance the gravitational force between the particles, enough to create a micro black hole.
Suddenly, the idea that the Earth might one day fall victim to a black hole doesn't seem quite so unlikely. If we are ever unlucky enough to meet one, what would it be like? It begins.
2 masses of the sun in the skies now. All right, so this should be enough for Earth to have a relatively perfect circular orbit around these 2 objects. And interestingly, what you can see right away is that the way that the sun orbits around the black hole means that anyone observing this from Earth would see sun move a little bit more across the skies than it should. And also, we wouldn't really see the black hole itself. It's too tiny, actually. It's only about 3 kilometers in radius. So in comparison to the sun's 700,000 kilometer radius, it would be just a speck of light coming, not a light, of darkness coming in front of the sun. So we wouldn't really see any difference, but we would feel the difference, and you're going to see how we would feel this difference in a few minutes. The way we will feel this difference is through temperature. As you can see, the temperature has started to actually drop, although maybe not. It's down to about 12.4 degrees Celsius here. This is what's been happening to our planet Earth. Basically, it's slowly turning into an ice bowl yet again. You can see the temperature every year is decreasing and is slowly falling lower and lower. There's also, if you actually look at individual fluctuations here, about every 4 days it goes up and down. It's cooler than in the actual Earth, even though, as you can see, the orbit is almost a perfect circle. And the reality is that it is actually due to these orbital fluctuations that are created by the black hole. As you can see, so typical Earth is in orbit around the edge of the habitable zone here. So it's in a slightly warmer region. But because of these fluctuations, this new Earth is now spending quite a lot of time in this region, which is a little bit cooler than the region it was in before. And so over time, the temperature on Earth here slightly drops by like a decimal point. And with time, this will add up to several degrees and possibly even go below zero because Earth will slowly keep cooling down.
And now we're going into a new orbit. And now we're going into a new orbit.
Yeah, I kind of like that last part. And now we're going into a new orbit. Yeah, almost like a Freudian slip from NASA there or something. But yeah, that was just a little something that I wanted to throw together of bits and pieces of different things that I've seen that kind of relate to it and may support a different idea for you know, the birth and progress of black holes and the possibility of black holes forming without a star going supernova and of stars actually being able to give birth to black holes without going supernova. So just something I thought I'd share. Let me know what you guys think about that if you care to comment. Thanks for watching your back-ass words weird world. See you later.